Hi guys, this is the EdExcel A-Level Maths Paper 1 from the October 2020 papers, and this paper covers the pure maths section. Question number 1. We have to find the first four terms in ascending powers of x of the binomial expansion of 1 plus 8x to the power of 1/2, giving each term in simplest form. Now, if you take a look in the formula book, the formula for the binomial expansion is shown highlighted here. And so using this formula, for part A, 1 plus 8x to the power of 1/2, that's approximately equal to 1, that's our first term, plus 1/2 multiplied by 8x divided by 1 factorial, that's our second term, plus 1/2 times by 1/2 minus 1 times by 8x squared all over 2 factorial, plus 1/2 times by 1/2 minus 1 times by 1/2 minus 2 times by 8x cubed all over 3 factorial. And then we have our higher order terms. And if we tidy all of this up, we've got 1 plus 4x, and here, if we work out this term here, we have 1/2 times by 1/2 minus 1 times by 8x squared over 2 factorial. That term here is minus 8x squared, and for the other term we have 1/2 times by 1/2 minus 1 times by 1/2 minus 2 times by 8 to the power of 3 divided by 3 factorial, which is 32. So we get 32x cubed. And then we have higher order terms as well. And now for part B, explain how you could use x equals 1 over 32 in the expansion to find an approximation for root 5. There is no need to carry out the calculation. For part B, to find out the approximation for root 5, given that x is equal to 1 over 32, we can substitute x equals 1 over 32 into both the left hand side and the right hand side. So when x is equal to 1 over 32, on the left hand side we have 1 plus 8 times by 1 over 32 to the power of 1/2. And if we work this out, here we have 1 plus 1/4 all raised to the power of 1/2, so that would be the square root of 5 over 2, which is, that would be the square root of 5 over 4, which is root 5 over 2. So here we have root 5 over 2, and on the right hand side, substituting x equals 1 over 32 into the right hand side, we have 1 plus 4 lots of 1 over 32 minus 8 lots of 1 over 32 squared plus 32 lots of 1 over 32 cubed. So if we work all of this out, we have 1 plus 4 lots of this minus 8 lots of this squared plus 32 lots of this cubed. That would be 1145 over 1024. So here we have 1145 over 1024. And therefore, we can see here that root 5 over 2, that's approximately 1145 over 1024. And therefore, to find out what root 5 is, we multiply this side by 2. So therefore, root 5, that's approximately equal to this value multiplied by 2, which is 1145 over 512. And the way I've set it out over here is the safest way to ensure that you get the marks required. Question number 2. By taking logarithms of both sides, we have to solve the equation 4 to the power of 3p minus 1 equals 5 to the power of 210. We have to give the value of p to one decimal place. So we begin with the 4 to the power of 3p minus 1, and this is equal to 5 to the power of 210. And if we take logs of both sides, it doesn't matter what the base is, as long as we take the same logarithm on both sides. For example, we can choose the natural log of x. So taking the natural log of both sides, we have ln of 4 to the power of 3p minus 1, and this is equal to the natural log of 5 to the power of 210. And if we power slide, we have 3p minus 1 lots of the natural log of 4, and that's equal to 210 lots of the natural log of 5. And if we divide both sides by the natural log of 4, we see that 3p minus 1 is equal to the natural log of, that's equal to 210 times by the natural log of 5 over the natural log of 4. And we therefore see that 3p, that's equal to this value plus 1, so let's work that out. We have 210 times by the natural log of 5 over the natural log of 4 plus 1, so 3p, that's equal to 244.80, etc. And therefore p, that's equal to this value divided by 3, which is 81.6. So we have 81.6 to one decimal place. Question number 3. Relative to a fixed origin O, point A has position vector 2i plus 5j minus 6k, point B has position vector 3i minus 3j minus 4k, and point C has position vector 2i minus 16j plus 4k, and we have to find the vector AB. So the vector AB for part A, that's equal to the vector OB minus the vector OA. So we have the vector OB, that's given by 3i minus 3j minus 4k, and then we subtract off the vector OA, which is 2i plus 5j minus 6k. And if we tidy all this up, 3i minus 2i, that would be 1i, minus 3j minus 5j, that would be minus 8k, and minus 4k minus 6k, that will be 2k. So we add on 2k. So this over here is the vector AB. And now for part B of the question, we have to show that the quadrilateral OABC is a trapezium, giving reasons for your answer. Well, let's quickly draw the trapezium OABC. So, having drawn the trapezium OABC, you can first of all recognize that AB is equal to 1/2 OC. In other words, we can conclude here that 2 times by the vector AB is equal to the vector OC. And therefore, in conclusion, we can see that OC is parallel to AB. Now, for us to show that we have a trapezium, if OC does not equal OB, even though they are parallel to each other, we can conclude that OABC is a trapezium. So first of all, let's work out the vector OC. Well, we already know the vector OC, we already know the vector AB, so let's work out the magnitude of AB and AC. We see that the magnitude of AB, that's equal to the square root of 1 squared plus minus 8 squared plus 2 squared. Turns out we get root 69. The magnitude of OC, that's equal to 2 squared plus minus 16 squared plus 4 squared. It turns out we get 2 root 69. And therefore we can conclude that since the vector AB does not equal the vector OC, we can conclude here OABC is therefore a trapezium. Okay. Question number 4. The function f is defined by f of x equals 3x minus 7 over x minus 2, where x is a real number and x does not equal 2. We have to find the inverse of f at the point x equals 7. First of all, we need to find out the inverse function, and then we can find out what happens when x is equal to 7. So, our first step would be to let y equal f of x. And if we do that, we have y equals 3x minus 7 over x minus 2. Our next step would be to rearrange for x. So if we rearrange for x, let's first of all multiply both sides by x minus 2. So we have y lots of x minus 2 equals 3x minus 7. Expanding on the left hand side, xy minus 2y, that's equal to 3x minus 7. Gathering all the terms involving an x on one side and everything that's not an x on the other side, we have xy minus 3x, which is equal to 2y minus 7. And if we factorize out an x on the left hand side, we have x lots of y minus 3, which is equal to 2y minus 7, and therefore x is equal to 2y minus 7 over y minus 3. Our next step would be to swap the x and y's. So if we do that, we have y equals 2x minus 7 over x minus 3. Okay? And our final step is to replace the y with the inverse of x. So replacing the y with the inverse of f, we can therefore conclude the inverse of x is equal to 2x minus 7 over x minus 3. This has a domain of x taking all real values and x not equaling 3. And now to find out the value of f of the inverse of f at the point x equals 7, this will be equal to 2 times by 7 minus 7 over 7 minus 3. So therefore, in conclusion, the inverse at the point x equals 7, that's equal to 7 over 4. And now for part B of the question, we have to show that f of x is equal to ax plus b over x minus 3, where a and b are integers to be found. So for this question, we would have to replace the x with 3x minus 7 over x minus 2. So f of x, that's equal to 3 lots of 3x minus 7 over x minus 2 minus 7 over 3x minus 7 over x minus 2 minus 2. And if we tidy this up, we can multiply both the top and bottom by x minus 2. So we have 3 lots of 3x minus 7 minus 7 lots of x minus 2 over 3x minus 7 minus 2 lots of x minus 2. And if we expand on the top, we have 9x minus 21 minus 7x plus 14. On the bottom, we have 3x minus 7 minus 2x plus 4. And therefore, we can conclude here f of x, that's equal to 2x minus 7 over x minus 3. Okay. Question number 5. A car has 6 forward gears. The fastest speed of the car in the first gear is 28 kilometers, and in the 6th gear, the fastest speed is 150 kilometers per hour. And given that the fastest speed of the car in successive gears is modelled by an arithmetic sequence, for part A, we have to find the fastest speed of the car in 3rd gear. So for part A, first of all, you need to recognise that an arithmetic sequence that's given by un equals a plus n minus 1 d, where n is the position, a is the first term, d is the common difference. And hopefully here you can see straight away that the first term is 28. So let's just write that down. We have a equals 28. And we can use this information in conjunction with this information here to find out the common difference, and then from that we can find the fastest speed of the car in the third gear. So we have 115, that's equal to A, that's 28, plus n minus 1 lots of d, so here we have 6 minus 1 lots of d. So from this we can find out what d is. So we have 115 minus 28, and then if we divide this by 5, we see that d is equal to 17.4. So with this we can find out what u3 is. u3, that's equal to 28 plus 3 minus 1 lots of 17.4, and if we work this out, so we multiply this by 2 and then add on 28, we get 62.8. So the fastest speed of the car in third gear is 62.8 kilometers per hour. And now for part B, we have to find the fastest speed of the car in the fifth gear, given that the fastest speed of the car in successive gears is modelled by a geometric sequence. And for a geometric sequence, we see that un, that's equal to a, that's our first term, multiplied by r, that's the common ratio, and we raise this to the power of n minus 1. So again, if we use the information given in the question for the sixth gear, we have 115 equals a, that's 28, multiplied by r, and we raise this to the power of 6 minus 1. So what we can hopefully see over here, r to the power of 5, that's equal to 115 over 28, and with this we can find out what r is. So if we work out the value of r, we have 115 divided by 28, and if we take the fifth root of this, so taking the fifth root of this, we come out with a value of 1.326, etc. So let's just store this value into our calculator. When we come to work out the fastest speed of the car in the fifth gear, we need to work out what u5 is. So u5, that's equal to a, that's 28, multiplied by r, that's 1.326, etc. And we raise this to the power of 5 minus 1. So if we work this out, so we have this to the power of 4 multiplied by 28, we get 86.7. So we get 86.7 kilometers per hour to 1 decimal place. Question number 6. For part A, we have to express sin x plus 2 cos x in the form r sine of x plus alpha, where r and alpha are constants, r is greater than 0 and alpha is in between 0 and pi over 2. We have to give the exact value of r and give the value of alpha in radians to 3 decimal places. In the formula book, we can use the compound angle formula shown here. Sine of a plus b is equal to sine a cos b plus cos a sine b. So we can express sin x plus 2 cos x in this form by rewriting this as the following. We have sin x plus 2 cos x, which is equivalent to r times by sine x times by cos alpha plus r times by cos x times by sine alpha. And we can find out the value of r and we can find out the value of alpha by comparing sines and cosines. If we compare the sine x's, on the left hand side we have one of them, and on the right hand side we have r cos alpha of them. Okay, and if we compare the cos x's on both sides, on the left hand side we have two of them, and on the right hand side we have r sine alpha of them. So we have 2 equals r sine alpha. And with this we can find out what alpha is, and we can do that by dividing the equations by each other. R sine alpha divided by r cos alpha, that would be tan alpha. Of course the r's cancel. 2 divided by 1, that's 2. And therefore alpha, that will equal the inverse tan of 2, which is 1.107. Let's store this into A. So alpha is equal to 1.107 to 3 decimal places. And the value of r, that's equal to 1 squared plus 2 squared square rooted. Turns out we get root 5. And therefore we can rewrite sine x plus 2 cos x as r, that's root 5, times by the sine of x plus 1.107. And now for part B of the question. The temperature theta degrees C inside a room on a given day is modelled by the equation theta equals 5 plus the sine of pi t over 12 minus 3 plus 2 times by the cosine of pi t over 12 minus 3, where t is in between 0 and 24, and t is the number of hours after midnight. And using the equation of the model and your answer to part A, we have to deduce the maximum temperature of the room in this day. And hopefully if we compare this result here with what we have in part A, hopefully you can see that the x's have been replaced with the pi t over 12 minus 3. And if we use our harmonic form given to us over here, then for part B you'd find theta to equal 5 plus root 5 times by the sine of pi t over 12 minus 3 plus the 1.107. And if we simplify all this, you'd find that theta is equal to 5 plus root 5 times by the sine of pi t over 12. Now here, if I subtract 3 from this and then store this into B, here we have minus 1.89, etc. Okay, so when we come to find out the maximum value of this result here, theta max, that will equal 5 plus root 5. And if that's not clear, I'll explain it using the graph here. In red over here, we've got the graph of sine t that has a maximum at 1, a minimum at -1. And the maximum occurs at pi over 2. So let's just add this in. This maximum over here has coordinates pi over 2, 1. And then once we find out what root 5 times by the sine of t plus 1.107 is, that's shown in blue, you'd find here the maximum is over here. It's translated 1.107 units to the left. So here we have the x coordinate of the maximum being at pi over 2 minus 1.107. And in terms of the y coordinates, you'd notice here we've stretched this graph by a scale factor of root 5 in the y direction. So the maximum here is at root 5. And then if you look at this graph in green, from this graph to this graph, we've then added 5 units on. So then this maximum over here, that will have an x coordinate of pi over 2 plus, well, we have to be a bit careful here. We have to apply this entire transformation onto pi over 2. Okay? So first thing we do, we add on 1.89 etc. to pi over 2. So we have pi over 2 plus 1.18 etc. And then we multiply this by 12, and then we divide the result by pi. So that's the x coordinate of the maximum point, and the y coordinate, that will be this root 5 plus 5. So here we have 5 plus root 5. Okay? Hence, the maximum is 5 plus root 5, as we see here. And don't forget your units. We have degrees C. And now for part C, we have to find the time of day when the maximum temperature occurs, giving an answer to the nearest minute. Well, of course, I've discussed all this before. Essentially, this maximum occurs at this point. So, we have pi over 2. So let's just write this down. We have pi over 2 plus this, and then we times this by 12. Then we divide this by pi. We get 13.23 etc. So therefore, the time will be 13.23 etc. So therefore, we have 13.1, well, we have to convert the 0.23 to minutes. So hours to minutes, so if I subtract off 13 and then multiply this by 60, turns out we get 13 hours 8 minutes. Okay, so we have over here 13:08 PM. Okay, so this is hours, and then we convert this into the minutes as well. Question number 7. We've got figure 1 over here which shows a sketch of the curve C with the equation y equals f of x, and we've got a straight line L. The curve C meets L at the points -2, 13 and 0, 25 are shown in this figure, and we've got this region R which is bounded by C and L, and given that f of x is a quadratic function in x, and this point -2, 13 is a minimum turning point, we have to use inequalities to define R. So, first of all, if we take a look at this straight line L, we can use y equals mx plus c to find out the equation of L. So, if we use y equals mx plus c, first of all, considering this point 0, 25, we have 25 equals m, lots of 0 plus c. Of course, c is equal to 25. Considering this point -2, 13, we have 13 equals -2m, so just write this down. We have m lots of -2 plus c. So therefore we have 13 equals -2m plus 25. We can conclude here m is equal to 6. And therefore the equation of L, we have y equals 6x plus 25. Okay? And if we consider our quadratic function f of x will be of the form a lots of x plus p all squared plus q. And at this point -2, 13, which is a minimum point, we have 13, rather, we have over here in complete the square form, we have a lots of x plus 2 all squared plus 13. So this is what f of x is. Okay? And this passes through the point 0, 25. So at the point 0, 25, we have 25 equals a lots of 0 plus 2 all squared plus 13. We can conclude here a is equal to 3. So therefore f of x, that's equal to 3 lots of x plus 2 all squared plus 13. And what we see over here, if we go back to the diagram, we see that R is above f of x, but it's below L. So we can use our knowledge of regions to define what R is. So as I've just said, R is above this 3 lots of x plus 2 all squared plus 13, but it's below 6x plus 25. And therefore, as an inequality, we've got 3 lots of x plus 2 all squared plus 13, which is less than y, which is less than 6x plus 25. And that makes sense, because here, this bit over here, below 6x plus 25 corresponds to this bit, but this thing above the 3 lots of x plus 2 all squared plus 13 corresponds to this bit. Okay. Question number 8. A new smartphone was released by a company. The company monitored the total number of phones sold, N, at time T days after the phone was released. The company observed that, during this time, the rate of increase of N was proportional to N, and we have to use this information to write down a suitable equation for N in terms of T. You do not need to evaluate any unknown constants in your equation. This is actually a very tricky question in my opinion. The first thing you need to notice, N is a function of T, and that's implied by this line over here and this line over here. N is in terms of T. So let's just write this down. N is a function of T. And let's just highlight this. Okay, so the number of phones sold, N at time T days after the phone was released. Now, what we see over here is that the rate of increase, so that tells us rate of increase, that's dn over dt, that's proportional to n. Okay, so the rate of increase of n, so that's dn over dt, that's proportional to n, as we see over here. So what that tells us is that dn over dt, that's equal to some constant a multiplied by n, where n of course is a function of t. Once we get to this stage over here, we now need to express n in terms of t. Okay, so we now need to express n in terms of t, and for us to do that we need to recognize what function do I have that when I differentiate it I get that function, and that's all this is saying. Once I differentiate n, okay, do I get essentially n again? Okay, and the only function that works for is e to the power of something. Okay, so therefore we have dn over dt, which is equal to a e to the power of kt. So here e to the power of kt is our function for n in terms of t. So i.e. n is equal to e to the power of kt. Okay? What I mean by this, when I differentiate this, I still get the function e to the power of kt, of course adjusting for the constants. But the important thing to notice over here, when I differentiate n, I still get n. Okay, and the only function that works for is e to the power of kt. So here k is a real number and a is also a real number. It's a very difficult question to understand, but you just have to recognize the property of e to the power of t. When I differentiate this, I get the same function. It's also worth pointing out k and a are both greater than 0 in this question. Okay, because we're increasing, so just bear that in mind. Question number 9. We've got figure 2 over here, which shows a sketch of the curve C with equation y equals f of x, and f of x is equal to 4 lots of x squared minus 2 lots of e to the power of minus 2x, where x is a real number. And we have to show that f dash of x is equal to 8 lots of 2 plus x minus x squared lots of e to the minus 2x. So for part A of the question, we begin by writing out what f of x is, which I'm going to rewrite as 4e to the minus 2x lots of x squared minus 2. And we can use the product rule to differentiate this. You'd find over here, using the product rule, u is equal to 4e to the minus 2x and v is equal to x squared minus 2. U dash, that will equal minus 8e to the minus 2x. V dash, that's equal to 2x. And therefore, using the product rule, f dash of x, that's equal to v, which is x squared minus 2, times by u dash, which is minus 8e to the minus 2x, plus u, which is 4e to the minus 2x, times by v dash, which is 2x. And if we tidy all this up, here we have minus 8e to the minus 2x x squared, and then we have minus 2 times by minus 8, that's plus 16. So we have plus 16 e to the minus 2x. And then here, 4 times by 2, that's 8. So we add on 8e to the minus 8, 8e to the minus 2x times by x. And if we factorize out an 8, and then factorize out an e to the minus 2x, inside this bracket we have minus x squared plus 2 plus x. And therefore we can conclude here f dash of x, that's equal to 8 lots of 2 plus x minus x squared lots of e to the minus 2x. And that's what we wanted to show. And now for part B, hence find in simplest form the exact coordinates of the stationary points of C. Now, whenever we see the word stationary points, we should instantly be thinking to ourselves, the first derivative is equal to 0. So, for part B, we have f dash of x, which is equal to 0. So we have 8 lots of 2 plus x minus x squared e to the minus 2x, which is equal to 0. And of course here, e to the minus 2x cannot equal 0. So therefore we have, if we divide through by 8 first of all, we see here we have 2 plus x minus x squared equaling 0. So from this, we can rewrite this. If we multiply through by minus 1, we have x squared minus x minus 2 equals 0, which if we factorize this, we have x minus 2 lots of x plus 1 equals 0. Of course, x is equal to minus 1 or 2. And with this, we see here, these are our x coordinates of the stationary point. We can now find out the corresponding y coordinates of the stationary point. And we can do that by substituting back into the original function here. So, f of minus 1, that's equal to 4 lots of, and if you go back here, we have x squared minus 2 lots of e to the minus 2x. So here we have x squared, so that would be minus 1 squared, that would be 1, minus 2. And then here we have e to the minus 2 times by minus 1, which is positive 2. And if we tidy this up, we get minus 4e squared. And f of 2, that's equal to 4 lots of 2 squared, that would be 4, then minus 2, then we multiply this by e to the minus 2x, so here we multiply by e to the power of minus 2 times by 2, which is minus 4. So here we end up with 8e to the minus 4. And therefore, these stationary points, those have coordinates minus 1, minus 4e squared, and also 2, 8e to the minus 4. Okay? And if we add these stationary points to the diagram, we see here we have this stationary point and this stationary point. And now for part C of the question, the function g and the function h are defined by g of x equals 2 lots of f of x, where x is a real number, and h of x, that's equal to 2 lots of f of x minus 3. And we have to find the range of g and the range of h. Okay. I think the best way to approach this question is to apply the transformations. So for the first part of part C, we've got g of x, which is equal to 2 times by f of x. And if you go back to what f of x is, if we multiply what we have over here by 2, because we have 2 lots of f of x, from that we can determine what the range is. So having drawn the graph, we multiply the stationary points, that is the y coordinates of the stationary points, by 2, and therefore we see over here that the range of g of x, that would be, in interval notation, minus 8e to the minus 2, sorry, minus 8e to the 2, this should be 2, infinity. Okay. So now for the next part, when we come to work out the range of h of x, bearing in mind h of x is greater or equal to 0, so this bit in light blue we're disregarding, we see that this time one of our stationary points, well, we still multiply by 2 as before, but this time we have to subtract off 3. Okay, so let's just move this down. So for the other part of the question, we have to recognize that h of x, that's equal to 2 times by f of x minus 3. Okay, so if we compare this to what we had before, here we had an asymptote at y equals 0, so therefore when we translate that by 3 units down, the new asymptote is at y equals minus 3. We subtract off 3 units from the y coordinate of this stationary point over here. So this time we're below the x-axis, so you can work that out on your calculator. This value is close to 1, so when we subtract off 3, we get a value over here which is around 2. Now when we come to work out the range, we first of all need to find out where it intersects the x-axis. Okay? And we can do that by setting x equal to 0. In other words, h of 0, that will equal 2 times by f of 0 minus 3. So we have 2 lots of 4 lots of 0 squared minus 2 lots of e to the power of 0 minus 3. So here we end up with 2 lots of minus 8 minus 3, which is minus 19. So therefore this point has coordinates 0, minus 19. And therefore you can hopefully see that the range of h of x in interval notation, that's minus 19, 16e to the minus 4, minus 3. Okay. Question number 10. For part A, we have to use a substitution x equals u squared plus 1 to show that the integral from 5 to 10 with respect to x of 3 over x minus 1 lots of 3 plus 2 lots of the square root of x minus 1 is equal to the integral from p to q with respect to u of 6 over u lots of 3 plus 2u, where p and q are positive constants to be found. Well, the first thing we need to do is apply our substitution. We have x equals u squared plus 1. From here we can rearrange to say that u squared, that's equal to x minus 1, and therefore u, that's equal to the square root of x minus 1. Next, we can differentiate x with respect to u. So dx over du, that's equal to 2u, and therefore dx, that's equal to 2u times by du. Now, when x is equal to 5, we can find out what the corresponding u limit will be. So when x is equal to 5, using this result here, u is equal to 5 minus 1 square rooted. 5 minus 1, that's 4, so we have the square root of 4, which is 2. And similarly, when x is equal to 10, u, that's equal to 10 minus 1 square rooted, which is 3. Of course we take the positive square root because p and q are both positive constants. So now we can rewrite our integral in terms of u. So we can see here that the integral becomes, well, here, instead of us having the limits 5 to 10, our new limits are from 2 to 3. And here we've got this 3. Now over here, x minus 1, hopefully you can recognise that's u squared. And here we have 3 plus 2 lots of the square root of x minus 1. The square root of x minus 1, that's u. And then dx, that was 2u du. So here we have 3 times by 2u over u squared lots of 3 plus 2u du, which if we tidy this up, we have the integral from 2 to 3 of 6 over u lots of 3 plus 2u du. And that's exactly what we wanted to show. P, that's equal to 3, Q, that's equal to 2. Okay? Sorry, got this the wrong one. P is equal to 2, Q, that's equal to 3. And now for part B, hence using algebraic integration, we have to show that this integral is equal to the natural log of a, where a is a rational constant to be found. And for us to integrate that, we'd have to use our result from part A, so we'd have to integrate this. Now integrating 6 over u lots of 3 plus 2u, that's a bit complicated. And the way we approach that is we can split this up into partial fractions. So for part B, we can split 6 over u lots of 3 plus 2u into partial fractions, and we'll do this in a different colour. We have 6 over u lots of 3 plus 2u. This is equivalent to a over u plus b over 3 plus 2u. And if we multiply both sides by u lots of 3 plus 2u, we have 6, that's equivalent to a lots of 3 plus 2u plus b lots of u. And to find the values of a and b, we substitute values of u into these brackets such that one of those brackets will eliminate. So if we let u equal 0, on the left hand side we have 6, and on the other side the b bracket disappears, so here we have a lots of 3. A is equal to 2. When u is equal to minus 3 over 2, we have 6, which is equal to minus 3 over 2b. B is equal to minus 4. Of course, the a bracket disappears. And therefore, we can conclude 6 over u lots of 3 plus 2u, that's equivalent to 2 over u minus 4 over 3 plus 2u. And therefore, we can replace this bit with what we have over here. So the integral from 2 to 3 with respect to u of 6 over u lots of 3 plus 2u, that's equivalent to the integral from 2 to 3 with respect to u of 2 over u minus 4 over 3 plus 2u. And here we have something of the form f dash over f. Now we can make the adjustments for the constants. So we have here 2 lots of 1 over u minus 2 lots of 2 over 3 plus 2u. Here we have something of the form f dash over f. So when we come to integrate, here hopefully you can see we have 2 lots of the natural log of the mod of u minus 2 times by the natural log of the mod of 3 plus 2u, and we're working this out in between the limits 2 and 3. Okay, so with that we can combine these together. So we're evaluating then here 2 times by the natural log of the mod of u over 3 plus 2u, and we're evaluating this in between 2 and 3. And if we substitute in our limits, for the upper limit we have 2 times by the natural log of 3 over, well here we have 3 plus 2 times by 3, that's 9. And then we subtract off 2 times by the natural log of 2 over 3 plus 2 times by 2, that's 7. So we subtract off 2 times by the natural log of 2/7. So here we can combine these logs together. So we have 2 times by the natural log of, well, 3 over 9, that's 1/3, and 2 over 7, well, we'll leave that as it is. And we can tidy this up even more. So we have 2 times by the natural log of 7 over 6, Okay, so let's just write this up neatly. So here we have 2 times by the natural log of 7 over 6, and then we can power slide the 2. So we have the natural log of 7 over 6 squared, 7 over 6 all squared, that would be 49 over 36. So in other words, A is equal to 49 over 36. Okay. Question number 11. Circle C1 has equation x squared plus y squared equals 100, and circle C2 has equation x minus 15 all squared plus y squared equals 40. They meet at the points A and B as shown in figure 3, and we have to show that the angle AOB is equal to 0.365 radians to 3 significant figures, where O is the origin. Well, hopefully here you can see that the centre is at the origin and the radius, that's equal to 10. And similarly here, hopefully here you can see that the centre, that has coordinates 15, 0, and the radius, that's root 40. So with this, to find out the intersection points, we need to solve these 2 equations simultaneously. So for part A, we've got x squared plus y squared equals 100. We'll leave that alone. And here, x minus 15 all squared, that would be... So okay, let me just be a bit more clear over here. The circle C1 has equation x squared plus y squared equals 100. The circle C2, if I expand the x minus 15 all squared, I get x squared minus 30x plus 225 plus the y squared, and this is equal to 40. And for me to solve this simultaneously, what I can do is rewrite this as x squared plus y squared equals 30x minus 185. The reason I want to do that, if we compare the left hand side here with the left hand side here, we can see that they're the same. So therefore, you can hopefully see, comparing equation 1 and 2, so comparing equation 1 and 2, you can hopefully see here we have 100, which is equal to 30x minus 185, and if we solve for x, we have here 100 plus 185 divided by 30, which is 19 over 2. Okay, and with this we can find out the corresponding y coordinates by substituting back into equation 1. So when x is equal to 19 over 2, we have 19 over 2 squared plus y squared, and this is equal to 100. So if I square this and then 100 minus this, y squared, that's equal to 39 over 4. Okay, and therefore y, that's equal to the square root of this, which is root 39 over 2. Okay, so what does this mean? Don't forget, when we square root we have plus minus. So this means that the coordinates of A, that's given by 19 over 2 root 39, over 2, and the coordinates of B, that would be 19 over 2 minus root 39 over 2. Okay? And therefore, if we think about what this means in terms of the diagram, it means that the length AB will be root 39. So the reason for that is here, the coordinates of A are 19 over 2 root 39 over 2, and the coordinates of B, that's 19 over 2 minus root 39 over 2. So the difference between these heights, if the x coordinates are the same, would be root 39 over 2 minus root 39 over 2, which is root 39. So here, AB is equal to root 39. Okay? Units. And for us to find the angle AOB, we can construct a triangle. So if we go back to our diagram, we know that the radius is 10. So we have 10 here and 10 here. And for this smaller triangle, the radius here is root 40. And here we have another root 40. And AB, that's root 39. Okay, so let's just add this in a different colour. Here we have root 39. Maybe if we do in this colour. So here we have root 39. Okay, and we're finding out this angle over here. And this angle we'll call this angle alpha. Okay, and we'll call this angle beta. So if we construct that triangle AOB, so just constructed the triangle over here. Okay, and obviously this point over here corresponds to the point D, and we already know the coordinates of D. That would be 15, 0. Okay, so going from here to this line AB, this length over here, 15 take away 19 over 2, that's 11 over 2. Okay, actually we don't need that. So for us to find out the angle AOB, we would have to use the cosine rule to find out the angle. So using the cosine rule, we have the cosine of alpha, which is equal to 10 squared plus 10 squared minus root 39 squared divided by 2 times by 10 times by 10. And if we work this out, we have 10 squared plus 10 squared minus 39 over 200, which is 161 over 200. Okay, and therefore the angle alpha, that's equal to the inverse cos of this, which is 0.635. Okay, radians. And let's store this in here just in case we need it later on. And now, the region shown shaded in figure 3 is bounded by C1 and C2. We have to find the perimeter, giving our answer to 1 decimal place. Well, for us to find the perimeter, we would have to first of all recognize here we have an arc and another arc. And if I can work out this larger angle, that will enable me to find out what the perimeter is. And for that, I need to find out what this angle beta is. So, again using the cosine rule, cos beta, that's equal to root 40 squared, okay, plus root 40 squared minus root 39 squared divided by 2 times by root 40, so 2 times by root 40 times by root 40. So here we have 40 plus 40 minus 39, that's 41, on the bottom we have 80. So here we have the inverse cos of 41 over 80. Okay, so that's 1.03. So here we get 41 over 80. So therefore beta, that's equal to 1.03, what was it, 1.032 radians. Okay, now the arc length, that's equal to the radius times by theta. Okay, so for us to work out the arc length, namely this one and this one, we need the arc length. Okay, we need this other angle over here, so we need this angle over here, and we also need this angle over here. Okay, so this angle, that's going to equal 2 pi minus beta, and this angle, that's going to equal 2 pi minus alpha. And then with that we can find out the arc length. Okay, so therefore the perimeter, that's equal to 10, which is the radius, multiplied by the angle, which I just said was 2 pi minus the 0.635, etc. And then we add on root 40, that's the radius of the smaller circle, and then we multiply this by 2 pi minus the 1.032, etc. So if we work all this out, so we got 2 pi minus this, and then we multiply this by root 40, and then we add on 10 lots of 2 pi minus minus a which is 89.68, etc. So to one decimal place, we can see that the perimeter is equal to 89.7 units to one decimal place. Question number 12. In this question, you must show all stages of your working. Solutions relying entirely on calculated technology are not acceptable. For part A, we have to show that cosec theta minus sine theta is equivalent to cos theta cot theta. Now, I recommend you all unsimplify the other side, and that will help you figure out some of the stages that you might need to use. So if you look at the right hand side for example, we've got cos theta cot theta. Now, cos theta cot theta, that's the same as 1 over tan theta. Okay? And 1 over tan theta, that's the same as cos theta over sine theta. So here we have cos theta multiplied by sine theta, multiplied by cos theta over tan theta. Cos theta over sine theta. And we can rewrite this as cos theta over 1. So here we get a cos squared theta over sine theta. Now, if during our working we get to this stage, then from here we can essentially work backwards to get to this step. So, for this proof, if we start on the left hand side, we have over here cosec theta minus sine theta. Cosec, that's the same as 1 over sine. So here we have 1 over sine theta minus sine theta. And we can combine these together. We can rewrite sine theta as sine squared theta over sine theta. So we have 1 over sine theta minus sine squared theta over sine theta. And we can combine these on the top. We have 1 minus sine squared theta. On the bottom, we have sine theta. Now 1 minus sine squared, that's cos squared. So here we have cos squared theta over sine theta, which is what we have over here. So now we can work backwards to get to this step. So cos theta we can rewrite as cos theta over 1 multiplied by cos theta over sine theta. So here we have cos theta times by cot theta. And hopefully you can see here that writing out this on the side of your page will help you figure out how to show the proof. So therefore, since the left hand side is equivalent to the right hand side, we have shown the identity. Okay. Now for part B of the question, hence or otherwise, solve for x being in between 0 and 180, the equation cosec x minus sin x equals cosec x lots of cot x, cot of 3x minus 50. Okay. Now, for us to solve this, of course, here, that is what we found here. So, for us to solve this equation, let's begin by writing it out. We have cosec x minus sin x equaling cos x cot of 3x minus 50. And if we use what we found in part A, on the left hand side we have cos x cot x, and this is equal to cos x cot of 3x minus 50. And straight away hopefully you can recognize that cos x equals 0 is a solution to this equation. The reason for this if we write this down in a different colour actually, we can take everything over to one side. So here we have cos x cot x minus cos x cot of 3x minus 50. We can factorise out a cos x. So we have cos x lots of cot x minus cot of 3x minus 50 equals 0. And then from this you should be able to see that cos x equals 0, or cot x minus cot of 3x minus 50 is equal to 0. Now if cos x is equal to 0, let's go on our calculator. The inverse cos of 0, that's 90 degrees. Okay, so from here you can hopefully see x is equal to 90 degrees. That's one solution. And now we have to deal with this over here. So let's just move this down. Let's now work with this over here. Okay, so here we can hopefully see that cot x, that's equal to cot of 3x minus 50, and cot, that's the same as 1 over tan. So here we have 1 over tan x, and that's equal to 1 over tan of 3x minus 50. And if I multiply 1 by this result and 1 by this result, we have over here tan x, which is equal to tan of 3x minus 50. Now to solve this, we would have to recognize that we have an equation of the form tan alpha equals tan beta, and I'll show you how to solve that sort of equation. Now over here, if we have tan of alpha equaling tan of beta, we can find out the general solution of an equation in this form. Of course, alpha, that's x, beta, that's 3x minus 50. But to solve an equation in this form, we have to rewrite this as sine alpha over cos alpha, and this is equal to sine beta over cos beta. And if I take everything over to one side, we have sine alpha over cos alpha minus sine beta over cos beta, and this is equal to 0, and we can combine these. So we have sine alpha cos beta minus cos alpha sine beta over cos alpha cos beta, and this is equal to 0. And if you take a look on the formula book, sine of a minus b, that's equal to sine a cos b minus cos a sine b. So using that, on the top we have sine of alpha minus beta, and on the bottom we still have cos alpha cos beta, and all this is equal to 0. So here we have sine of alpha minus beta, which is equal to 0, and if I take the inverse sine to find out what alpha minus beta is, alpha minus beta, the inverse sine of 0, that's 0. And if you think about the graph of sine, let's quickly draw that. Hopefully here you can see that sine of alpha minus beta equals 0 implies that alpha minus beta is equal to 0, 180 or 360. And you'll notice each time sine of something equals 0 for the following. For 180, lots of pi. Sorry, 180 lots of n, okay? That makes sense. So no matter what values of n I choose, provided n is an integer, okay, let's just specify this, for n being an integer, sine of something will always be 0, okay? Provided n is an integer. So with that, what this implies over here, if I just move this for a second, what this implies over here is that alpha, that's equal to 180 lots of n plus beta, okay? That's a general solution. So this is for n being an integer, okay? And therefore we can conclude over here that the general solution for tan of alpha equaling tan of beta, that would be alpha equals 180n plus beta for n being an integer, okay? So with that, how does this help us? Well, I said before that x is alpha over here and beta, that's 3x minus 50. So if we write that down, we have over here tan x equals tan of 3x minus 50. So if I inverse tan both sides, or match it up with what I have over here, we see that x is equal to 180n plus 3x minus 50. So in other words over here, alpha, that's equal to x, beta, that's equal to 3x minus 50. Okay? So with this we can find out what x is, and I recommend you all draw the graph for this. So I recommend you draw the graph of tan x and the graph of tan of 3x minus 50 in the required range to solve this equation and to see which solutions you actually need. So here I've drawn the graph of tan x and the graph of tan of 3x minus 50. Now over here somewhere I have some sort of an asymptote, okay? So let me just add this asymptote in like so. So here I've got an asymptote at x equaling 90, so that's for tan x, and here the graph crosses at 0 and it also crosses at 180, okay? And if you look at the other graph, we're going to have an asymptote somewhere over here, like so, and we're also going to have another asymptote here somewhere, okay? Now to find out the equations of those asymptotes, well, we just have to apply the transformation to x equals 90. So here we have 90, let's get the calculator, so here we have 90 plus 50, and then if I divide this by 3, I get 46.046, etc. So here I've got x equals 46 and 2/3. And for the other asymptote, well, this next asymptote occurs at 270. So 270 plus 50, and then dividing this by 3, we end up with 106.6, etc. So here we've got x equals 106 and 2/3. So that's that done. So those are those graphs, okay? And of course we've got another asymptote here somewhere, okay? And if you want to figure out that asymptote, well, 270 plus 180 plus 50 divided by 3, that's 166 and 2/3. So here we've got x equals, what was it? X equals 166 and 2/3. So that's this asymptote. This asymptote corresponds to this, and this asymptote corresponds to this. And we can even do the -1 as well, but let's just leave that for now. But clearly, the solutions we want in between x equaling 0 and 180, we want this solution here. So we want this over here, and we also want this solution here. Okay, so these are the solutions we want. So we can find those out by substituting different values of n into here. Now clearly, let's start off with n equaling 0. So when n is equal to 0, we've got x equals, well, this term goes to 0 and we're left with 3x minus 50. So therefore, x over here is equal to 25. So therefore here, we've got x equaling 25. And let's see what happens when n is equal to 1. So here we have x equaling 180 plus 3x minus 50. And if we find out what x is, well here, let's just tidy this up a bit. We've got 2x equaling, well, 180 minus 50, that's 1/3. Taking that to the other side, we get minus 130. So therefore x is equal to minus 65. That minus 65 corresponds to this over here. Okay, so here we get minus 65. And we don't want that because it's not in the required range. Now let's see what happens when n is equal to minus 1. We've got x, which is equal to minus 180 plus 3x minus 50. So here we've got 2x. That's equal to, well, here we've got minus 230. Taking that to the other side, we get 230. So therefore, x is equal to 115. So here we get x is equal to 115. So therefore, our solutions to this problem, we've got x is equal to 0, that's one solution, x equals 25, and x equals 115. And hopefully you can see how the graph helps to visualize what solutions we require. Question number 13. A sequence of numbers a1, a2, a3, etc. is defined by a n plus 1 equals k lots of a n plus 2 over a n, where n is a natural number and k is a constant. And given that the sequence is a periodic sequence of order 3 and a1 is equal to 2, we have to show that k squared plus k minus 2 equals 0. So what we have over here for part A, we've got a n plus 1, that's equal to k lots of an plus 2 over an. Okay, and we know that a1, that's equal to 2. a2, using the sequence, that's equal to k lots of a1 plus 2 divided by a1. So here we've got k lots of 2 plus 2 over 2, and we can simplify this to 2k. a3, that's equal to k lots of a2 plus 2 divided by a2. So here we've got k lots of 2k plus 2 divided by 2k. And if we tidy all this up, we get k plus 1. And we can continue with this. The reason I want to continue, if we have a periodic sequence of order 3, this suggests to us that a1 is equal to a4, which is equal to a7, etc. So we want to find out what a4 is and set them equal to each other. So therefore, continuing, a4, that's equal to k lots of a3 plus 2 divided by a3. So we have k lots of k plus 1 plus 2 divided by k plus 1. And if I tidy all this up, I get k lots of k plus 3 over k plus 1. Okay. And we know that a1 is equal to a4. We mentioned that here for a periodic sequence of order 3. So we can therefore say that a1, which is 2, that's equal to a4, which is k lots of k plus 3 over k plus 1. So we have 2 lots of k plus 1 equaling k squared plus 3k. So therefore 2k plus 2 is equal to k squared plus 3k. Of course, we can conclude over here that k squared plus k minus 2 is equal to 0. Now for part B of the question, for this sequence we have to explain why k cannot equal 1. So if we assume here that k is equal to 1, our first term, that would be 2. Our second term, we can see here that would be 2 times by 1, which is 2. Our third term, that would be 1 plus 1, which is 2. And our fourth term, that will be 1 lots of 4 over 2, which is 2. And what we see here, when k is equal to 1, all the terms are the same. So for k equals 1, all the terms would be the same. So in other words, all the terms will equal 2, so the sequence would not have a period of order 3. And now for part C of the question, we have to find the sum from r equals 1 to r equals 80 of AR. Now over here, let's first of all solve this equation to find out what k value we should use. So here we've got k plus 2 lots of k minus 1 equaling 0. So therefore k is equal to minus 2. That's our only solution. And that's because k cannot equal 1. Okay, so that's why we only take this solution over here. Now if k equals minus 2, let's see what we get. So if k equals minus 2, a1, that will equal 2, that's not going to change. a2, that will equal 2 times by minus 2, which is minus 4. And a3, that will equal minus 2 plus 1, which is minus 1. And of course, because we have a period of order 3, a4, that will equal a1, which is 2. Okay, so let's just write all this down. So we want to find this out. So first of all, we see that a1, that's equal to 2. Okay, a2, that's equal to minus 4, and a3, that's equal to minus 1. And because we have a period of order 3, a1, that's equal to a4, a2, that's equal to a5, a3, that's equal to a6, and we can continue this. So a7, a8, and a9 can be determined, so can a10, so can a11, and so can a12. And we can continue this. But at what point do we stop? We want to essentially find out the last value to use. Or we can do it by brute force. We can actually sum all the terms, but there's an easier way of doing it. There's 80 terms we're adding together. And because we have a period of order 3, certain terms will repeat a certain number of times. And the question is, how many times does 2 repeat? How many times does 4 repeat? Sorry, how many times does minus 4 repeat? And how many times does minus 1 repeat? So, for us to determine that, 80 divided by 3, that would be 26 2/3. So here, 2 repeats 26 times, minus 4 repeats 26 times, and minus 1 repeats itself 26 times. And then the 2/3, that just tells us that a1 is being repeated an extra time and a2 is being repeated an extra time. So with this, we can find out what the last term will be over here, being repeated 26 times. So here, 2, 4, 7, etc. If we want 26 terms here, here we want 25. Similarly here, if you want 26 terms, this will be 26. And here, if we want 26 terms, here we have 27. Okay? So what does this mean? Let's just write it down. So here, the 2, the minus 4, and the minus 1 are being repeated 26 times. And we see here, for this first row, we have 26 terms. For the second row, we have 26 terms. For this third row, we have 26 terms. And then we have an extra 2 and an extra 4. And we saw that from here, where we have the 2/3. So the 26 times by 3, that will be 78. So the 78th term, that will be a27. And then a28, that will be the 79th term, and a29, that would be the 80th term. And remember, here we've got 80 terms. So we have 26 lots of 2 minus 4 minus 1 plus an extra 2 and an extra minus 4. So let's just highlight all this. We have 26 lots of this, which indicates that the 2, the minus 4 and the minus 1 are repeated 26 times. And then we've got this extra 2 and this extra minus 4. And if we work all of that out, it turns out we get minus 80. So therefore, the sum from r equals 1 to r equals 80 of AR, that's equal to minus 80. Question number 14. A large spherical balloon is deflating. At time t seconds, the balloon has radius r centimeters and volume v centimeters cubed. The volume of the balloon is modelled as decreasing at a constant rate, and using the model we have to show that dr over dt is equal to minus k over r squared, where c is a positive constant, where k is a positive constant. Well, the volume of a sphere, okay, so a large spherical balloon, that tells us that the volume that will be given by v equals 4/3 pi r cubed. Okay, so let's just write this down all for part A. We've got v, which is equal to 4/3 pi r cubed. And with this, we want to find out what dr over dt is. So that suggests to us that we're going to use the chain rule. And if you look in the question, we're told that the volume of the balloon, that's decreasing at a constant rate. So that tells us that dv over dt, that's decreasing, so we have a minus, at a constant rate. We'll call this rate c. So constant rate, that tells us we have a c. Decreasing, we have that, okay, and perhaps we've got the word rate, so that suggests to us that we have d over dt, okay. So that's quite helpful, because now that suggests to us we can use the chain rule. Why do we want to use the chain rule? Well, if we know that dv over dt is equal to minus c, we want to find out in this question dr over dt. Okay, so for us to do that, we can first of all find out what dv over dr is. dv over dr, that's equal to 4 pi r squared, and therefore dr over dv, that's equal to 1 over 4 pi r squared. And using the chain rule, dr over dt, that's going to equal dr over dv multiplied by dv over dr. It's as though these dv's cancel out. So we have dr over dv, that's 1 over 4 pi r squared multiplied by dv over dr. Sorry, here we have a t, multiplied by dv over dt, which is minus c. So therefore, here we get minus c over 4 pi r squared, which is the same as minus k over r squared. The reason for that, this k over here, that's the same as c over 4 pi. We have a number divided by another number, which is simply a constant. And that's exactly what we wanted to show. Now for part B of the question, given that the initial radius of the balloon is 40 centimeters, and after 5 seconds the radius of the balloon is 20 centimeters, and the volume of the balloon continues to decrease at a constant rate until the balloon is empty, we have to solve this differential equation to find a complete equation linking r and t. Well, for part B, for us to solve this differential equation, let's just write out the differential equation first. We have dr over dt, which is equal to minus k over r squared. First thing we need to do is separate the variables. So multiplying through by r squared, we have r squared dr, which is equal to minus k dt. And then if we integrate both sides, we see that we have r cubed over 3, which is equal to minus kt plus some constant. We'll call this constant a. And we already know from the question the initial radius of the balloon is 40 centimeters. So that tells us that when t is equal to 0, r, that's equal to 40. So substituting this into here, we have 40 cubed divided by 3, that's equal to minus k lots of 0 plus a. So therefore we can hopefully see a, that's equal to 64,000 over 3. Okay, so far we can see that r cubed over 3, that's equal to minus kt plus 64,000 over 3. And we also know from the question, after 5 seconds, the radius of the balloon is 20 centimeters. So when t is equal to 5, the radius, that's equal to 20. So here we have 20 cubed over 3, that's equal to minus 5k plus 64,000 over 3. So therefore, if we solve for k is equal to minus 11200 over 3. And knowing the value of k and knowing the value of a, we can therefore conclude r cubed over 3, that's equal to minus 11200 t over 3 plus 64,000 over 3. And if I multiply through by 3, r cubed, that's equal to 64,000 minus 11200 t. And that's our equation. Now for part C of the question, we have to find the limitation on the values of t for which the equation in part B is valid. So we have to find a range of values of t and then comment on that. And obviously, time can't be negative. So for part C, the model is only valid for t being greater than 0, and obviously we can't have a negative volume. So also, the volume can be 0, but the radius can be 0, meaning it's completely deflated, but it can't be less than 0. So the model is only cubed for r cubed being greater or equal to 0. In other words, we have 64,000 minus 11200 t being greater or equal to 0. So therefore t is greater or equal to 40 over 7 seconds, and therefore the full range of values, we have 0 which is less than or equal to t, which is less than or equal to 40 over 7 seconds. Question number 15. The curve C has equation x squared tan y equals 9, where y is in between 0 and pi over 2. And for part A, we have to show that dy over dx is equal to minus 18x over x to the 4 plus 81. So for this, we would have to use the product rule. If we say that u is equal to x squared and v is equal to tan y, we can use implicit differentiation to find out what dy over dx is. So if I differentiate, well, here we have v this is the best way of explaining it. First of all, let's just copy out the question. We have x squared tan y, which is equal to 9. And for this, there's no y's involved. So let's just start off by differentiating. We have we have v times by u dash, so we have tan y, multiplied by u dash, which is 2x, plus u, which is x squared, multiplied by v dash, differentiating tan y with respect to x, that would be sec squared y dy over dx. And differentiating 9, we end up at 0. So we have 2x times by tan y, and this is equal to, and we add on, sorry, x squared sec squared y dy over dx. And this is equal to 0. And if you notice in the question, there's nothing involving a sec squared or a tan y. So essentially we want to eliminate these. And whenever we have something involving trig, we have to think of our identities. We should know that 1 plus tan squared a, that's equivalent to sec squared a. So that will help get rid of this sec squared y, but I'll still have this. If I get rid of that, I'll still have something involving a tan y. What I mean by that, here we have 2x times by tan y plus x squared lots of 1 plus tan squared x times by dy over dx. And this is equal to 0. Sorry, tan squared y. I still want to get rid of this tan y. And if you look over here where we have x squared equals, sorry, x squared lots of tan y equals 9, we can actually rearrange that, which will tell us what tan y is, and that will help us eliminate all these tan y's. So from here, we can see that x squared is equal to 9 over tan y. And now if we substitute this into here, we would have 2x lots of, well actually, if x squared is equal to 9 over tan y, we can therefore conclude here that tan y is equal to 9 over x squared. So now we can substitute this into here. That's what we're supposed to say. So we have 2x lots of 9 over x squared plus x squared lots of 1 plus tan squared y. So here we have 1 plus 9 over x squared squared. And then we multiply this by dy over dx. And this is equal to 0. So now we just have some algebra to work through. Well, here we have 18 over x. That's quite straightforward so far. And then here, if I multiply the x squared into here, we're going to have x squared. Now here 9 over x squared squared, that would be 81 over x to the 4. And if I multiply that by x squared, we end up with 81 over x squared. And this is being multiplied by dy over dx. So just pay attention to where your brackets are. And obviously this is equal to 0. So dy over dx, that's equal to, if I take this over to the other side, we have minus 18 over x divided by x squared plus 81 over x squared. And now we just need to simplify all this, and the way we can do that is multiplying each term through by x squared. So now we're going to multiply through by x squared, and if we do that, minus 18 over x times by x squared, that would be minus 18x. And on the bottom, x squared, let's write this out, x squared times by x squared, that's x to the 4. And then we have 81 over x squared times x squared, which is 81. So therefore, dy over dx, if I write it out neatly, we have minus 18x divided by x to the 4 plus 81. And now for part B of the question, we have to prove that C has a point of inflection at x equals the fourth root of 27. Now point of inflection, this suggests to us that we need to find out what d squared y over dx squared is. And for a point of inflection, d squared y over dx squared is equal to 0. So for part B, we need to work out d squared y over dx squared, and that's equal to the differential of dy over dx. So we will need to differentiate what we have over here, the minus 18x over x to the 4 plus 81. And for us to do this, we'd have to use the product rule. Sorry, we have to use the quotient rule. U is the thing at the top, V is the thing at the bottom. So U, that's equal to minus 18x. V, that's equal to x to the 4 plus 81. Now U dash, that's equal to minus 18. V dash, that's equal to 4x cubed. So working out d squared y over dx squared, that will equal if we see over here that u and v is equal to dy, where u is equal to dy and v is equal to dx, we see over here that dy over dx, that's equal to v u dash minus u v dash over v squared. It's in the formula book somewhere. So we have v, that's x to the 4 plus 81, times by u dash, which is minus 18, minus u, which is minus 18x, times by v dash, which is 4x cubed. And then we divide this entire result by v squared. So we divide by x to the 4 plus 81 squared. And if we tidy all this up, what we can do over here is multiply this x by this x cubed, which will get us an x to the 4. So here we have x to the 4 plus 81, lots of minus 18, minus and a minus give a plus. So we have plus 18 lots of 4x to the 4. Okay? And on the bottom, we have x to the 4 plus 81 squared. So, for us to simplify all this, well, here, let's factorize out a minus 18. So we have minus 18 lots of, here we have x to the 4 plus 81 minus 4x to the 4, and then we divide this entire result by x to the 4 plus 81 squared. So here we've got minus 18 lots of minus 3x to the 4 plus 81 divided by x to the 4 plus 81 squared. Okay? And if I multiply this negative into the bracket, we can therefore conclude that d squared y over dx squared, that's going to be equal to 18 lots of 3x to the 4 minus 81 over x to the 4 plus 81 squared. That's quite useful for us. For a point of inflection, we check what happens to the second derivative either side of this value. Now, if we work out that value, so here we have the 4th root of 27, that's 2.27, etc. So this value over here, that's 2.27, etc. So just bear that in mind. We're going to check a value below this value and a value above this value. So what do I mean by that? Well, over here, first of all, let's set d squared y over dx squared equal to 0. And when we do that, we have 18 lots of 3x to the 4 minus 81 over x to the 4 plus 81 squared, and this is equal to 0. So here we have 3x to the 4 minus 81, which is equal to 0. X to the 4 minus 27 is equal to 0. So therefore, x is equal to the 4th root of 27. So that's where the point of inflection occurs. Let's confirm this. Okay, so we can do this by substituting values, as I said, above this value and below this value. So if you look at this value, which is 2.27, etc. Let's see what happens when x is below this value of 2.27, etc. For example, let's choose x equals 2. If we work out what the second derivative is at this point, we have 18 lots of 3 times by 2 to the 4 minus 81 divided by 2 to the 4 plus 81 squared. So if we work this out, we have 18 lots of 3 times by 2 to the power of 4 minus 81 over 2 to the power of 4 plus 81 squared, which is minus 594 over 9409. And what you see over here, this value is less than 0. So therefore we have something which is concave. And when x is equal to 3, something above this value, d squared y over dx squared, that's equal to 18 lots of 3 times by 3 to the power of 4 minus 81 over 3 to the power of 4 plus 81 squared. And if we work this value out, so let's just change this to a 3. And here, let's also change this to a 3. We end up with 1 over 9. And we see that this is greater than 0, so therefore we have something which is convex. So therefore we can conclude the following. So we're going from something which is concave to convex, and we saw that the second derivative equaling 0 implies that x is equal to the 4th root of 27, and therefore the 4th root of 27 is a point of inflection. So I should be technical over here. Let's just complete this properly. Therefore, x equaling this is a point of inflection. Question 16, we have to prove by contradiction that there is no positive integers p and q such that 4p squared minus q squared equals 25. Now with a proof by contradiction sort of question, we first of all assume the opposite. So we will assume that there is a positive integer p and q such that 4p squared minus q squared equals 25. Now this we can write as a difference of two squares. So we have 2p plus q lots of 2p minus q equals 25. And if you think about the factors of 25, we have the following. We have 1, 5 and 25. So here, what we're saying 1 times by 25, that's 25, or 5 times by 5 is 25. So with this we can form a couple of equations. So if true, we have 2p plus q equaling 25. That could be one bracket, and the other bracket could be the 1. So we have 2p minus q equals 1. And if we solve these simultaneously, we get p equals 6.5 and q equals 12. Similarly, if this bracket is 1 and this bracket is 25, we still get p equals 6.5, q equals 12. Or we can have both brackets being 5. So we have 2p plus q being 5, and 2p minus q being 5, so we have 5 times by 5. And if we solve those simultaneously, we get p equals 2.5 and q equals 0. But we said over here, p and q are positive integers, so we have a contradiction. So we have a contradiction, so there's no integer solutions. So for our conclusion, there's no positive integers p and q such that 4p squared minus q squared equals 25.